This video is going to be about the Initial Value Theorem. It is highly related to continuous. It's actually usually in the same section where you introduce continuity, but it is kind of a separate concept, so we're going to do it a little bit separately. And so the Initial Value Theorem says that suppose f is continuous on some interval from a to b, and let n be any number between f of a and f of b. And what the Initial Value Theorem says is then there exists a number in C that's in AB such that f of C is equal to whatever that number n was. And so picture-wise, what this is showing you is here's some n here, here's some function, here's a and b. F of b is here, f of a is down here, and what it's saying is there is some number that's between f of b and f of a. So you can see n is between these two numbers on this axis. And there is some number c such that f of c is in fact n. So it's known as the Initial Value Theorem. There's a couple of things I want to point out about this. The first thing is that there can be multiples. So here we are from a to b. There actually are multiples places where it crosses, but because we're between a and b, we would only have the one c. There's multiple places where it can happen, but we only care about between a and b. So this is the first thing to realize, is that you can have multiple places where it happens, but make sure you're looking at your domain that you're dealing with. The other thing about this idea is that it has to be continuous. So if your function is not continuous, and that's why we talk about this when we deal with continuity, if here's f of a and here's f of b, here's a and b and here's f of a and f of b, and you have some number between those, but you're not continuous, then we could have some big separation here and there is no function value. So do be careful about that. You must have continuity to have this happen. As an example, here we have an a and b. If n equals 0, n is equal to 0 is somewhere between f of a and f of b, then you can see there is some c where that will happen. If you have a different n of, let's say, 5, it's still between f of a and b, then you have a different c that's between a and b where that would happen. So let's go ahead and prove that x squared equals the square root of x plus 1 has one real root in the interval from 1 to 2. So that's what we want to look at. So let's look at this function. Let's actually make it into a function. Right now it's an equation, x squared equals the square root of x plus 1. If we want a root, we're looking for x squared minus the square root of x plus 1 equal to 0. So we're looking for where this expression equals 0. And then we can say, well, that expression is my function. So f of x is the x squared minus the square root of x plus 1. So we're looking to see where does f of x actually equal 0, somewhere in between 1 and 2. So first off, we have to look at the fact is it continuous? So remember, we must be continuous, because if we're not continuous, you can put a number between f of a and f of b, but you don't get a function value because the function was continuous. So our first thing is to say, is this continuous? So let's look at that. So f of x is continuous on the interval from 1 to 2, since, first off, the square root of x plus 1 is continuous on there. Because if you were to look at this, put 1 in there, 1 plus 1, you get the square root of 2. Put 2 in there, you get the square root of 3. And x plus 1 has to be greater than or equal to 0. And so everything works out. X squared is always continuous. So remember, x plus 1 has to be greater than or equal to 0. So x has to be greater than or equal to 1, negative 1 actually. So we're definitely continuous from 1 to 2 because x is continuous. F of x, the square root of x plus 1 is continuous on the interval from negative 1 to infinity. So we're definitely continuous from 1 to 2. So good, we are continuous. We know that. That's cool. That's good. So now what we have to do is find out what is f of 1. f of 1 is 1 squared minus the square root of 1 plus 1. So it's 1 minus the square root of 2. 1 minus the square root of 2 is a number less than 0. Because remember, we're looking at the interval from 1 to 2. So we want to look at what happens at those endpoints. We know we're continuous, so we're now just going to look at the endpoint. So let's look at f of 2. So we have 2 squared minus square root of 2 plus 1 is 4 minus square root of 3. Well, 4 minus square root of 3 is actually going to be a number bigger than 0. So therefore, by the intermediate value theorem, there exists a number C in 1, 2, such that f of C equals 0. So remember, all we were trying to do is show that has one root. We weren't asking you to find it. We were just trying to show that there was one root. We have now shown that there is one root in between 1 and 2. So we're all good. We've got that proven. All right, one last thing we can do with that is, now that we know there is a root, let's find it. So let's find that root to, let's say, 2 decimal places. We already know that f of 1 is less than 0 and f of 2 is greater than 0. So therefore, we know the root is in 1, 2. Not great, but at least we got that much. We know it's somewhere between 1 and 2. We don't know exactly what, but we know it's somewhere between 1 and 2. So let's see if we can get a little bit closer. Let's see if we can maybe go closer and get a little bit bigger. So let's look at 1.1. See if we can get a little bit more exactness. If I put 1.1 in, I still get a number less than 0. If I put 1.2 in, I still get a number less than 0. If I put 1.3 in, I suddenly get a number bigger than 0. So that tells me that the root is in 1.2 to 1.3. So instead of just being between 1 and 2, I now know, hey, it's just between 1.2 and 1.3. So I get a little bit more exactness of what my root might be. And so now, let's see if we can get even better. So we know it's between 1.2 and 1.3. So let's just try 1.22. When I use 1.22, I get a number that's still less than 0. If I use 1.23, again, I'm just making these numbers get a little bit closer together with each other. More. Now I still get a number bigger than 0. So now that tells me, by the intermediate value theorem, that my root is in 1.22 to 1.23. Okay, so let's see if we can get even better. If we wanted to do decimal places, we have 1 decimal place of green and the whole number green. Let's see if we can get 2 decimal places. So again, if I do 1.220, that number was less than 0. If I do 1.221, that number is greater than 0 all of a sudden. So that tells me my root is in 1.220 to 1.221. So these now agree to 2 decimal places. So I can now tell you that the root is approximately 1.22, because we've agreed to that many decimal places. And that's one of the uses of the intermediate value theorem.